In this video, we're going to be going over how to do the calculations for a weak base strong acid titration when you've reached the equivalence point. You can tell that we're at the equivalence point before even starting because we have the same volume and the same molarity for each one of our chemicals. So there's going to be an equal number of moles. Okay, so the first thing I want to do is set up my fake rice table where we'll put all of the moles for each chemical, and I will write the reaction. So we'll have our weak base, ammonia, plus our strong acid, which I will abbreviate as H+, so that we can have a net ionic equation to make our ammonium ion. Okay, so for initial moles, all I have to do is take the liters of the base, 0.025 liters, and multiply that by the 0.1. And do the same calculation for the H+ to see that our change is going to be all of these moles so we'll have none of our weak base left at this point. And all of it will have turned into the conjugate acid, the ammonium ion. Okay, so now that we have the moles of our product, our ammonium ions, we need to see what that concentration is going to be so I can stick it into a real rice table later to see what's happening. So I know I've got 25 plus 25 milliliters. That means that my new total volume is 50 milliliters. When you change that into liters, it's 0.05. And so I will do the moles of the ammonia divided by the 0.05 liters to get 0.05 molarity, understanding that I didn't save my sig figs. There's a bunch of zeros after that. Now, before we get started, we need to remember what exactly is in our beaker. After this titration, we're going to have 0.05 molarity, just ammonium ions. But we need to remember that all of the solutions for this chapter are dissolved in water. So we also have waters floating around. Now the ammonium ion, when it's by itself in solution, will donate its proton every once in a while to one of the water molecules, which lowers the pH just a little bit. So if you set up this rice table, we can assume that we have none of our products. We're starting with 0.05 molarity of the ammonium ion, small change in X, like really, really small, and we'll have plus X for both of the other species. Now, I don't particularly care how much of my ammonia I make, but I do care how much of the hydronium ions I make. Those are the same thing as H+, and those will control the pH change that we're looking for. So now, I just need to set up my K expression using the Ka this time because the ammonium ion acts as an acid. And either, if you have access to a textbook, you look up the Ka value, or you can use a really nifty equation, the Kw equals Ka times Kb, to find the Ka. I happen to have this particular one memorized because I use it so often. It is 5.6 times 10 to the negative 10. And we'll set that equal to x squared. We'll use our 5% rule to ignore this x, put 0.05. When you solve for the x, you end up getting 5.29-ish times 10 to the negative 6 if you save all of your sig figs. And then all you have to do is remember what pH actually means. In this problem, we just need to take the negative log of our x value. So we'll hit the negative log button, take the negative log of that answer, realize that we need to have 2 sig figs in our answer. 5.28 will be our final pH. Now for some people this is kind of weird, but similar to our weak acid videos, the pH at the equivalence point for titrating a weak acid or a weak base is not going to be 7. This is because the products of that titration are weak acids and bases themselves. So you need to know that when you're titrating a weak base, the equivalence point will probably have a pH lower than 7.